Hello students, welcome to part 2 of our video lecture on gravitation, which is given in chapter number 8 of physics for class 11. In the previous session, we studied about Kepler's laws, universal law of gravitation and the gravitational constant. In today's session, we will study acceleration due to gravity of Earth, acceleration due to gravity below and above the surface of Earth, gravitational potential energy, and escape speed. We will also quickly go through some of the questions that are likely to be asked in your examination and competitive examinations. The solutions are very brain taxing and you have to go through it thoroughly and practice it again and again and listen my lecture very carefully and with apt attention. I welcome you once again. Note down all the important points. Acceleration due to gravity. The Earth can be considered to be a sphere made of large number of concentric spherical shells with smallest one at the center and the largest one at the surface. A point outside the Earth is obviously outside all the shell. Thus, all the shells exert a gravitational force at the point outside just as if their masses are concentrated at their common center according to the result stated in our previous sections. The total mass of all the shells combined is just the mass of the Earth. Hence, at a point outside the Earth, the gravitational force is just as if its entire mass of Earth is concentrated at the center. For a point inside the surface, inside the Earth, the situation is different. This is illustrated in the figure shown on the screen. The force of attraction exerted by Earth on a body is called gravitational pull or gravity. The acceleration produced in the motion of a body under the effect of gravity is called acceleration due to gravity, and it is denoted by the letter or by symbol small g. If capital M subscripts E equals mass of the Earth and R subscripts E equals radius of the Earth and G is the acceleration due to gravity, then gravitational force between a body and Earth is given by F. Force F is equal to capital G into capital M subscripts E into small m divided by capital E R square. Here capital M subscripts E is the mass of Earth. ME represents mass of the Earth and RE represents the radius of the Earth. As usual, F will be the force and capital G is the gravitational constant. Therefore, the gravitational pull, that is the weight acting downward, is W is equal to M into G. We know that weight is equal to mass into gravitational force. So that is equal to mg is equal to force. Therefore, small mg equals, we can write F, putting the value of F, mg is equal to capital G into me into small m divided by Re square. Therefore, from this we can find the value of G. So here m on the left side and right side get cancelled. What remains is capital G me divided by R square. Putting their values and substituting, that is a gravitational constant 6.67 into 10 to the power of minus 11 into mass of Earth 6 into 10 to the power of 24 kgs divided by 6400 into 10 to the 10 cube whole square, that is equal to, we get the value as 9.8 meters per second. You substitute and simplify the values and note down all these important points. Now we will find the relationship between small g and capital G. Small g is gravitation, acceleration due to gravity, and capital G is gravitational constant. Therefore, small g is equal to G, capital G, me by re square. So mass of earth we will substitute is me is equal to 4 by 3 pi into re cube rho, where rho is the uniform density of the material of the earth. Therefore G is equal to, we get 4 by 3 pi into rho g into re. So re square cube gets cancelled and only re remains. Simplifying, we get g is equal to 4 by 3 pi rho capital G into re. Let it be equation 3. Its value depends upon the mass radius and density of the planet, and it is independent of the mass, shape and density of the body placed on the surface of the planet. Acceleration due to gravity is vector quantity and its direction is always towards the center of the planet. And dimensions of small g, acceleration due to gravity, equals L into t to the power of minus 2. That is the dimensions of acceleration. And its average value is taken to be 9.8 meters per second square, or 981 centimeters per second square on the surface of the mean sea level. Here in this point number 1, you please note that it depends on mass, radius and density of the planet, but it does not depend on any mass or shape or density of any other body placed on the surface of the body. This difference you kindly underline. Acceleration due to gravity above the surface of Earth. In the previous slide, we studied about acceleration due to gravity on the surface of the Earth. In this case, 8.6.1, we will study about the above the surface of the Earth. Please see the diagram. Consider a body at this point which is at a height h. This is the shape of the Earth and re is the radius of the Earth here. Therefore, consider a point mass m at a height h above the surface of the Earth as shown in the figure on the screen. The radius of the Earth is denoted by r subscript e. Since this point is outside the Earth, its distance from the center of the Earth is re plus h. So, from the center of the Earth, the height of the object is re is this radius plus h. If f of h denotes the magnitude of the force on the point mass m, here it is the point of mass small m, we get the equation force is given by mod of f, vector f is equal to capital G into m1 m2 divided by r square. This is the basic formula for force. We have to remember force between two bodies of mass m1 and m2 is given by F is equal to capital G into m1 into m2 divided by r square. That can be written as, here in this case particular surface of the Earth, Fh equals G into mass of Earth. M suffix E is the mass of Earth and small m is the mass of the body which is external to the surface of the Earth, divided by Re, radius of the Earth plus height square. The acceleration experienced by point mass is Fh by m. So here that is equal to G into h. We get G of h is equal to f of h by m. That is, if we divide capital Fh by small m, then we get the value of gh as capital G m e divided by re plus h whole square. Let it be equation 3. This value is less than g on the surface of the earth. Therefore, g is equal to g into me, mass of earth, divided by re square. So the mass gets reduced by Re square in the denominator. Therefore, if for H less than Re, if it is inside less than because H is very small than the radius of the earth. If H is the value of H is smaller than very small than Re, then we get G of h is equal to at a height, that is acceleration due to gravity at a height h is equal to G into me divided by Re square into 1 plus h into Re whole square, h divided by Re whole square. Therefore, that is equal to G into 1 plus h by Re whole to the power of minus 2. Therefore, let it be equation 4. If h is at a very large distance and move greater than Re, then h is approximately is equal to G into 1 minus 2h by Re. Let it be equation 5. From equation 5 thus tells us that for smaller heights, that is case number 4, above the value of G decreases by a factor 1 minus 2h divided by Re. Next section. Acceleration due to gravity below the surface of the earth. In section 8.6.1, we studied about the acceleration due to gravity above the surface of earth. In this section, we will study about acceleration due to gravity below the surface of earth. So here consider a mass m which is at a distance d from the surface of earth. This outer radius in the circle is the surface of the earth, and this mass is at a depth of d from the surface of the earth. Now consider a point mass m at a depth below the surface of the earth, so that its distance from the center of earth is Re minus d. So this full radius is Re. Now the depth is reduced by d. Therefore, new depth is Re minus d as shown in this figure. The earth can be thought of as being composed of small spheres. This is a sphere, small sphere of radius Re minus d and a spherical shell of thickness d. We can consider this as a spherical shell of thickness d. Therefore, the force on the m due to outer shell of thickness d is 0, because we have studied it earlier in the previous section. That is, the force on m due to the outer shell of thickness d is 0. The force due to this shell is 0. Therefore, as far as the smaller sphere, so ms, that is inside, this is within the dotted line, Re minus d is concerned, the point mass is outside it, and hence according to the result quoted earlier, the force due to smaller sphere is just as if the entire mass of the smaller sphere is concentrated at the center, because of this dotted line sphere, the mass is concentrated at the center of the Earth, center of the sphere. If ms is the mass of the smaller sphere, as shown here, ms, then ms by me, that is mass of sphere, small sphere, divided by mass of Earth is equal to Re minus d whole cube divided by Re cube. Let it be equation 6. Thus, the force on the point of mass is F of d is equal to G into ms, capital Ms into m divided by R minus d whole square. This is we had derived earlier. Let it be equation 7. Substituting for ms from this equation, we can write Fd, force at a depth d, equals G into me. So therefore, me, substituting for ms, simply for ms, ms is the me into m into Re minus d divided by Re square. Let it be equation 8. Therefore, G is equal to F of d divided by m. That is, if we divide equation 8 by m, we get the value of acceleration due to gravity at a depth d. That is equal to G into me divided by Re cube into Re minus d. That is equal to rewriting G into Re minus Re. Re minus d divided by Re, because G into me divided by R square is G, the value of G on the surface of the Earth. G is the gravitational acceleration on the surface of the Earth. Therefore, that can be written as G into 1 minus d divided by Re. That is, if you divide the term within brackets by Re, we get 1 minus d by Re. Let it be equation 9. Thus, as we go down below the Earth's surface, the acceleration decreases, underline decreases by a factor 1 minus d by Re. The remarkable thing about acceleration due to gravity, Earth's gravity, is that it is maximum on the surface of the Earth, decreasing when you go up or you go down. So, if you go up from the surface of the Earth, the value of gravity, acceleration due to gravity, decreases. Similarly, you go down below the surface of the Earth, then also the value of gravitational acceleration decreases. Gravitational potential energy. We know that the potential energy is the energy stored in a body at a given position. If the position of the particle changes on account of forces acting on it, then the change in its potential energy is just the amount of work done on the body by the force. These forces, for which the work done is independent of the path, are the conservative forces. The force of gravity is a conservative force, and we can calculate the potential energy of a body arising out of these forces. Hence, the gravitational potential energy of a body at a given point in a gravitational field of another body is defined as the amount of work done in bringing the given body from infinity to that point. Please note, the potential of a body, the potential energy of a body is in the gravitational field of another body. This is very important point. And the gravitational potential energy between two bodies of masses capital M and small m separated by a distance r is given by the formula capital U is equal to minus of capital G capital M into small m divided by r, where U is taken to be 0 as r tends to infinity. If the distance becomes infinity, then will be 0. Gravitational potential energy is a scalar quantity. Its dimensional formula is ml square into t to the power of minus 2, and SI unit of potential energy, gravitational potential energy, is joules, represented by the symbol letter J. The gravitational potential energy of a body of mass m at a height h above the surface of the earth is given by the relations U of h is equal to minus capital G, capital M E, small m divided by R E plus h. Here G is the gravitational constant, M E is the mass of Earth, and small m is the mass of the body under consideration, and R E is the radius of Earth, and h is the height above the surface of the Earth. The gravitational potential energy of a body of mass m on the surface is given by Us is equal to U of suffix x, S represents the surface, is equal to minus G capital ME m divided by Re. Here in this equation, that is, for surface of the earth, h is 0. On the surface of the earth, h is 0. You also know that F is equal to mg. Consider points close to the surface of the earth at a distance from the surface much smaller than the radius of the earth. In such cases, the force of gravity is practically a constant equal to mg, that is, F is equal to mg, directed towards the center of the earth. If we consider another point at a height h1 from the surface of the earth, and with respect to another point vertically above it at a height h2 from the surface, the work done represented by W12 equals force into displacement, that is equal to mg into h2 minus h1. The change in potential energy when the body of mass m is moved vertically upwards through a height h is equal to h2 minus h1 from the surface of the earth is given by the relation delta U. Delta U is the change in potential energy equals UH minus US, that is potential energy at a height h minus potential energy at the surface of the earth, given by the formula G into ME M divided by RE minus G into ME into M divided by RE plus H. Therefore, simplifying, that becomes delta U is equal to G into ME MH divided by RE square into 1 plus H divided by RE. You please simplify the terms within the big bracket. Therefore, that becomes, further it becomes, if we write G into ME divided by R square in these terms equal to small g, that is acceleration due to gravity, then delta U is equal to mgh divided by 1 plus h into Re. If the value of h is very small as compared to radius of the earth, that is h smaller than Re, then delta U is equal to mgh. Let us do a worked example on potential energy, gravitational potential energy. Question number 1. Find the potential energy of a system of 4 particles placed at the vertices of a square of side L. Also obtain the potential at the center of the square. Please read the question again and note down. See, the diagram is shown on the screen. Here, a square of side length L is shown with 4 sides. Mass m is placed at the vertices of each corner. That is m, m, m and m. And the diagonal is also shown here. So these m is placed at the four corners and length. So if you calculate the length of the diagonal, it becomes using Pythagoras theorem, you will get the length of diagonal. Let us solve it. Answer. Consider four masses or each of mass m at the square side L as shown in the figure below. We have four masses pairs at the distance L and two diagonal pairs at a distance 2L. Therefore, the work done is WR is equal to minus 4 into G into M square divided by L due to four masses. This first part on the right hand side is due to four masses M, that is 4 into Gm square by L. And in the diagonal we have two masses which is at a distance of root 2L. Therefore, that is equal to minus 2 into Gm square divided by square root of 2 into L. Therefore, that is equal to 2 into Gm square divided by L into 2 plus 1 by root 2. That is simplifying. Therefore, for we can write it, the substitute, the simplify the values of 2 plus 1 over root 2 into 2 as minus 5.41 into Gm square by L. Therefore, the gravitational potential at the center of the square is center of the square is the distance is r is equal to center of the square is at a distance r from one corner equals r equals root 2L divided by 2. This we have to find out using Pythagoras theorem. Find out the length, diagonal length, and then divide it by 2. You will get r is equal to root 2L divided by 2. Therefore, UR will be is equal to at a distance R will be equal to minus 4 into square root 2 into Gm divided by L. Escape speed. The escape speed on Earth is defined as the minimum speed with which a body has to be projected vertically upwards from the surface of the Earth so that it just crosses the gravitational field of Earth and never returns on its own. That means escape speed. Sometimes it is also called loosely called as escape velocity. Escape speed is the minimum speed with which a body has to be thrown vertically upwards from the surface of the earth so that it overcomes the gravitational field of earth and it does not return to earth on its own. This is the definition of escape speed. If V subscript E, VE is the required escape speed, then VE is given by the formula V subscript E equals square root of 2 into G capital M divided by R. Here VE is the escape speed, capital G is gravitational constant, M is the mass of Earth or mass of planet, and R is the radius of Earth. So we can substitute the value of mass as volume into density. Hence, this term can be written as 2g into volume into density divided by r. That is equal to 2g into 2g divided by r. Take common volume of a sphere. If you take it, it is given by the formula physical dimensions 4 by 3 into pi r cube into rho, where r is the radius of earth and rho is the density. 4 by 3 pi r cube is the volume of the earth. Therefore, simplifying, we get escape speed as square root of 8p into rho into g into r square divided by 3. Please remember it. You practice it again and again and you will be able to remember this formula. Therefore, V can be written as VE equals, that is escape speed of the planet can be written as square root of 2g into r, 2 of small g. Escape speed is independent of mass and direction of the projection of the body. So, it is independent of the mass of the body and direction of the projection of the body from this equation. Therefore, for Earth, V escape speed is equal to 11.2 kilometers per second. That is, from the surface of the Earth, if you throw a body at a speed of 11.2 kilometers per second vertically above, then the body will never return to Earth. A planet will have atmosphere if the velocity of molecule in its atmosphere is less than escape speed. That is why Earth has atmosphere while Moon has no atmosphere. So, if the velocity of the molecule in the atmosphere is less than the escape speed, then it will be visible. It will have an atmosphere. Whereas in Moon, there is no atmosphere. If a body is projected from a planet with a speed of v less than escape speed, then body will reach a certain height and may move in an orbit around the planet or may fall back to the planet. If the speed of projection is greater than escape speed, the body will escape out of the gravitational field of that planet and will move in the interstellar space with speed of v dash is equal to square root of v square minus ve square. Question number 2. Two uniform solid spheres of radii capital R but mass capital M and 4m have a center to center separation of 6r as shown in the figure below. The two spheres are held fixed. A projectile of mass m is projected from the surface of the sphere of mass m directly towards the center of the second sphere. Obtain an expression for the minimum speed of the projectile so that it reaches the surface of the second sphere. See here in the diagram below, two spheres of equal radii r. This is also r and this is also the radius is r. These two spheres are having. But mass of the first sphere is capital M, whereas the mass of second sphere is 4m. It is given. And the distance between them is 6r. So we have to obtain, the question is expression for, and there is another mass projectile m, small m, okay, that is projected from the surface of the sphere of mass m towards the sphere of mass 4m, second sphere. So we have to find the expression for the minimum speed. Let us do it. The projectile is acted upon by two mutually opposing gravitational forces of two spheres. The neutral point N, here as shown in the figure, is defined as the position where the two forces cancel each other. So at point N, the forces cancel each other. Therefore, if Yn is equal to R, Yn is equal to R, then we have Gm into small m by R square is equal to 4G into capital M small m divided by 6R into R whole square. Therefore, comparing and cancelling the common terms, we get 6R square is equal to 4R square. 6R minus R whole square is equal to 4R square. That implies 6R minus R, 6 into capital R minus small r is equal to plus or minus 2R. That is square root of 4R square is plus or minus 2R. So therefore, we will get two values of small r. That is R is equal to 2R or R is equal to minus 6R. This small r is also shown in the figure here. The neutral pair, the neutral point R is equal to minus 6R may be neglected. This value can be neglected because it is negative. Thus, Yn is equal to 2 into capital R. Small r is 2 into capital R. It is sufficient to project the projectile with a speed that will enable it to reach N. Thereafter, the gravitational pull of the 4m will suffice. The mechanical energy at the surface of capital M, mass capital M, is given by EI is equal to half mv square minus G capital M into small m by R minus 4gm into m by 5r. At the neutral point N, the speed approaches 0. This is, we are equating the mechanical energy, total mechanical energy at the point N. Therefore, that is EI is equal to half mv square minus gm into m by r minus 4gm into m by 5r. Therefore, the mechanical energy at N, point N, is purely potential energy. Therefore, En will be equal to, so this half mv square kinetic energy can be neglected. Therefore, En will be equal to minus gm into small m by 2r minus 4gm into m by 4r. Therefore, from the principle of conservation of mechanical energy, we get half v square is equal to gm divided by r minus 4 into gm by 5r. Simplifying that, this equation we are equating it to 0 and we get that is equal to minus 4 gm by 2r minus gm by r. That is equal to v square is equal to 2gm by r into 4 by 5 minus half. That implies v will be equal to square root of 3gm divided by 5r. This we have to simplify. Please write down step by step and you do it yourself and you will find the answer as v will be equal to velocity will be equal to square root of 3 capital Gm capital G capital M divided by 5r. Now we will continue with questions and answers of 1 mark, as these may be asked in your academic examination. Question number 1. The mass of moon is 10% of the mass of Earth. What will be the gravitational force of Earth on the moon in comparison to the gravitational force of the moon on the Earth? Answer. Both the forces will be equal in magnitude, as the gravitational force is mutual force between Earth and Moon, that is two bodies. Question number 2. Why does one feel giddy while moving on a merry-go-round? Answer. When moving in a merry-go-round, our weight appears to decrease when we move down, and it appears to increase when we move up. This change in weight makes us feel giddy. Question number 3. Name two factors which determine whether a planet would have atmosphere or not. Answer. The first factor is the value of acceleration due to gravity. And the second factor is surface temperature of the planet. Question number 4. The force of gravity due to Earth on a body is proportional to its mass. Then why does a heavy body not fall faster than a lighter? So the question I will read once again. The force of gravity due to Earth on a body is proportional to its mass. Force is proportional to mass, that is ma. Then why does a heavy body not fall faster than a lighter body? This is the question. Answer. We know that F is equal to G M capital M into small m by R square. So in this capital G is the gravitational constant and capital M is the mass of one body. So from this equation F is proportional to small m, but G is equal to Gm by R square. Therefore, small g does not depend on m, and hence the bodies fall with the same acceleration due to gravity small g. Question number 5. The force of attraction due to a hollow spherical shell of a uniform density on a point mass situated inside is 0. So, can a body be shielded from gravitational influence? No. The answer is no. The gravitational force is independent of intervening media. Question number 6. The gravitational force between two bodies is 1 Newton. If the distance between them is doubled, what will be the force between them? Answer. It is given that gravitational force, capital F is equal to 1 Newton. Therefore, F dash is equal to F by 4. That means the distance between them is double, means it is R square. So double means 2R, that is F by 4. So F dash will be, when the distance is doubled, the new gravitational force will be 1 by 4th of N, 1 by 4th Newton. Question number 7. A body of mass 5 kg is taken to the center of the earth. What will be its mass, first mass and weight there at the center of the earth? Answer. So mass does not change because m remains same wherever it goes. Whereas W weight is given by m, W is equal to m into G. G is 0 at the center, hence its weight will be 0. Question number 8. Why is gravitational potential energy negative? Because it arises due to attractive forces of gravitation. Question number 9. Identify the position of Sun in the following diagram if the linear speed of the planet is greater at C than at D. Please see the figure here. 2 points are given A and B, and the the rotation is, the planet is around the Sun. So the question is the position in which the linear speed is greater. So because if the Sun is closer to point C, that is at point B, its speed will be higher. That is the answer. Sun should be at the position B, as the speed of the planet is greater when it is closer to the Sun. Question number 10. A satellite of small mass burns during its descent and not during its ascent. Why? We have not studied about the satellite, which we are going to study in our next video, that is in part number 3. At that time, we will answer this question. Question number 11. If the density of the planet is doubled without any change in its radius, how does G change on the planet? Answer. G gets doubled as G, small g, is proportional to rho the density. Hence, when density of the planet is doubled, the value of acceleration due to gravity also is doubled. Question 12. Why the weight of the body at poles is more than the weight at equator? Explain. We know that G is equal to acceleration due to gravity. G is equal to Gm by R, where G is the gravitational constant, M is the mass of Earth, and R is the radius of Earth. The value of R at pole is less than the equator. So G at poles is greater than G at the equator. Now Gp, gravitation at pole, is greater than Ge at the equator. Hence, mass into Gp is greater than Ge, that is weight of the body at the poles is more greater than weight at the equator, that is mgp is greater than mge. Question number 13. A binary star system consists of two stars A and B which have time periods Ta and Tb, radius Ra and Rb, and masses Ma and Mb. Which of the three quantities are same for the stars? That justify. Answer. The angular velocity of binary stars are same, that is Wa is equal to Wb, where omega, it is not W, it is omega A equals omega B. That implies the time period of A is equal to time period of B. Question number 14. The time period of satellite of Earth is 5 hours. If the separation between Earth and satellite is increased to 4 times the previous value, then what will be the new time period of satellite? This question also we will answer in the next session. Question number 15. Why does the Earth impart the same acceleration to everybody? Answer. The force of gravitation exerted by Earth on a body of mass small m is given by F is equal to capital G capital M into small m divided by R square, that is equal to small m into G. That is the value of small g is Gm by R square. Therefore, G does not depend on, the small g does not depend on small m. Hence, the Earth imparts the same acceleration to all bodies. With this, we come to the conclusion of Gravitation Part 2. Next, we will take up Gravitation Part 3, where we will study Earth satellites, energy of an orbiting satellite, geostationary and polar satellites, and weightlessness. Till then, goodbye.